video, I will present my Bachelor Degree Project 2 entitled Application of Response Surface Methodology for Absorption of Methylene Blue Dye from Aqueous Solution using Orange Pale Waste. The release of dyes into the environment has induced many detrimental effects on all forms of life. Methylene blue is a widely used synthetic dye that contains heavy metals such as copper, zinc, lead, and chromium. Consequently, prolonged exposure to methylene blue dye will engender multiple health problems such as vomiting, nausea, and abdominal disorder. Adsorption is one of the effective methods to remove dyes. There are many different adsorbents available in markets such as zeolites, alumina, and clay. Nowadays, many natural materials are being employed to produce adsorbent. For instance, Rosa and his team has modified the rice husk waste to produce an adsorbent that could be utilized to remove cationic dyes from water. In this study, a quadratic model was developed to describe the influences of pH and contact time on the efficiency of methylene blue dye removal through the implementation of response surface methodology. Response surface methodology is a tool commonly used to design and optimize a process that is governed by various independent variables. It includes a series of statistical and mathematical techniques. At the end of the study, the optimum pH and contact time for the absorption of methylene blue dye by orange pale waste was determined. The objective for this study are to develop the regression model that portrays the relationship between the response and the independent variable for the absorption of methylene blue dye by orange pale waste. To evaluate the significance of the independent variables and to verify the adequacy of the developed regression model. To study the interaction between the independent variables and their influences on the response through the three-dimensional response surface plot and the contour plot, and to identify the optimal condition for the absorption of methylene blue dye by orange pale waste. This study intends to optimize the dye absorption process, which aims to show that the desired removal efficiency can be achieved by operating under optimum conditions. With this, modification of natural adsorbents, which may require additional costs, may not be needed. Next, I want to talk about the methodology of this study. First of all, a preliminary study was performed to obtain the relevant experimental data from a preceding study about the absorption of methylene blue dye by orange pale waste. Next, the data was imported into the design expert software for analysis. The historical data design was employed as the experimental data was acquired from existing research papers. After that, model selection was performed to choose the most suitable model that could describe the relationship between pH, contact time, and the efficiency of methylene blue dye removal. The analysis of variance was then utilized to verify the significance and fitness of the selected model. At the same time, the regression equation for absorption of methylene blue dye in terms of coded factors was generated. Various diagnostic plots were generated to validate and check the adequacy of the model. Moreover, the contour and three-dimensional response surface plots were also generated to explore the interactive effect resulted from pH and contact time on the efficiency of methylene blue dye removal. Lastly, numerical optimization was performed to identify the optimum condition for methylene blue dye elimination. Next, I want to present the results of my study. As we can see from the first figure of the result section, the quadratic model is suggested to be the most suitable model. Based on the table, it shows that the quadratic model has a sequential p-value less than 0.05 and a predicted R-squared value as high as 0.9877, which indicate that the quadratic model is significant. The high predicted R-squared value indicates that the model managed to predict the response value adequately. On the other hand, the high R-square value implies a good correlation between the predicted response and the actual experimental response. Based on calculation, the difference between the adjusted and predicted R-square value is 0.0018, which is within the desired range of 0.2. The small difference between the adjusted and predicted R-square values denotes that they are in good agreement with each other and prove that the model has high predictability. Therefore, the quadratic model is selected as suggested by the software to model the adsorption of methylene blue dye by orange pale waste. Next, let's move to the ANOVA table. ANOVA is utilized to justify the fitness of the quadratic model. As we can see, the quadratic model has a high F-value of 978.08 and a p-value less than 0.0001. Both of the values prove that the chosen quadratic model is significant. Furthermore, the result of ANOVA shows that all the model terms are significant and influential to the methylene blue dye removal efficiency due to their large F-value and small p-value. pH has the most significant impact on the efficiency of methylene blue dye removal as it has the highest F-value. Besides, the quadratic model has a high adequate precision, which shows that the signal is adequate for optimization in which all the predicted data are within the experimental range. In overall, the result of ANOVA analysis confirm that the quadratic model fits the experimental data very well. Next, let's look at the graph of predicted response value versus the actual response value. Based on the graph, the predicted removal efficiency is in good coincidence with the actual response. The high correlation between the predicted and actual response value indicates that the model has a sufficient capability to predict the response values. Then, let's look at the contour and response surface plots. The graphs show that the removal efficiency will increase when pH and contact time increase. The escalation of removal efficiency due to the increase of pH value can be explained by the electrostatic interaction between the cationic methylene blue dye and the negatively charged adsorbent surface. At low pH, the hydrogen ions of the acidic medium will compete with the dications for the adsorption sites on the surface of the adsorbent. Consequently, the removal efficiency is low when the pH value is low. Besides that, it is also suggested that the changes in pH value will alter the adsorbent surface properties. For instance, the number of negatively charged binding sites will increase when the pH value increases. On the other hand, when the contact time is long, there is more time for the dyes to form bonds with the molecules on the adsorbent surface. The dications may not have enough time to build an attraction with the adsorbents when the contact time is short. As time proceeds, the available adsorption sites are saturated with the dye molecule at a maximum removal efficiency of 81.27% is achieved. In this study, numerical optimization was performed to determine the optimum pH and contact time for the adsorption of methylene blue dye by orange pale waste to achieve a maximum removal efficiency. The predicted optimum pH and contact time are 9 and 360 minutes respectively, in which a maximum removal efficiency of 81.958% is achieved with a desirability function of 1. In conclusion, a quadratic model is created to elucidate the impacts of pH and contact time on the efficiency of methylene blue dye removal by orange pale waste. The optimum pH and contact time are 9 and 360 minutes respectively. This study successfully demonstrated that RSM can be employed to model and optimize methylene blue dye absorption by orange pale waste.